This is a sort of a continuation from last month when I told you that we were planning to do a very exciting occultation observation, an attempt to observe 14 Irene, big Irene as we know her now, blocking out a star. Now, Irene is not your normal asteroid. This is a biggie, hence the low number, one of the first 20. And we were successful in observing this. I'll show you fairly quickly how that went. It was a lot of fun. And then on Monday of this week, we had another one that came up. We've been doing these asteroid occultation observations for about 1.5 years. Our very first one was in October 2023, and it was the asteroid 785 Zwatana, 50 kilometers across. She's back, and I thought, well, we can't miss that one. So we managed to get a few volunteers together, including Beth, for her first asteroid occultation. We did observe this one too. So anyway, so this is some quick slides telling you what we did, why we did it, and things like that. Here's my beloved telescope, which I bought through Noah's assistance back in October, and it's now my standard go-to. It's an 8-inch Ritchie Chrétien, you don't really pronounce it like that, I just like saying it, astrograph with a GPS-powered camera stuck to the end. It's got guiding attached to it. It's got a laser pointer fashionably attached to the bottom, because I couldn't find anywhere else to hook it up. It's sitting on a Celestron CGE mount, all operated by a refurbished Windows 10 CPU. So with a GPS-powered camera, you can do precise, accurate measurements of times, like down at the millisecond and well below level. And that's what the people who run these occultation measurements really like to have, is some precise experimental data on where the asteroid really was in its orbit. Right. That's my garage. That's Lost Ridge Observatory.
That's your garage.
Yeah, that's my garage.
Very nice.
So this is Big Irene, Saturday night, 22nd March. Here's the solar system at the time, nothing particularly unusual. You can see the inner solar system out to Mars, and then with a slightly funny tilt, you get to Irene's orbit. Ordinary asteroid belt asteroid was about 2 AU away at the time of the event. I've kind of abbreviated this so I could get to 2 of them and not just one. Now, the group that you join is called IOTA, for the International Occultation Timing Association, and they have programs that let you generate trajectories of shadows of asteroids that are going to be crossing your location. So you can see where you are in the path, how close you are to the edge or the center, things like that. Like you might want to reposition yourself. So this is where we are at Tau, and in this case, the midline of the path of the shadow is the green line, and the 2 edges where they expect them to be are the blue and red lines, 1 sigma, 2 sigma standard deviations. Now, Irene is a biggie. She's a big lady, 150 kilometers in diameter.
Did she sing?
We sang after we saw her in her honor.
That's right.
So this shadow stretches from near Tau all the way up to southern Kentucky. Sort of hard to avoid this one. Now, since we were out on the edge, you won't see it for the expected maximum duration, which was predicted to be 11.2 seconds. If you assume a spherical asteroid and say I'm just seeing a slice, plug in the numbers, that should be more like 6.5 seconds. Still, that's very long. Usually these occultations are 1 second, 2 seconds, 3 seconds. So this one was a quite impressive event. And the star was really bright too. Usually the stars that are being occulted by the asteroid are 11th, 12th, 13th magnitude. You have to really stretch to see them. And you would really like to take a short frame so you've got a rapid, high resolution time description of what's going on. Just you go out and then come back again. So it's you really like to have a brighter star being occulted, but that's unusual. This was a very bright star. This was 9.5 magnitude. You can almost see it in good binoculars. So with a decent telescope at all, you can actually do some fairly good timing of when this event happens. Now this is, here's another amazing thing. This is the day of the event. Look at that beautiful blue sky. No clouds, no nothing. So everything was working well for us. And so you get it all set up, you're ready for it. This is Rob about half an hour before the event, waiting for it to appear, trying to keep the mead pointing in the right direction, which is a struggle. We were also joined by Bob Edwards and Jim Lord. This was Jim's first occultation. We were happy to see him there. And this is what one should see, according to my favorite sky simulation program, the SkyX. At just the right time, which is in the upper left, 11:00:34, you should see sitting right on top of the star, TYC Yakety Yakety, 9.5 magnitude. It should be blocked out by 14 Irene. 14 Irene was actually 11th magnitude, so the star doesn't vanish completely like it usually does. It drops in brightness to about 30%, because you're really just seeing the asteroid, nothing else. So you know the coordinates, everything like that. Let me get my laser pointer here. I need to point at things. So you know the coordinates, where this will happen from the program you get from the Occultation Society, right there. You know when it's going to be. They said sometime between 11:00:32, 11:00:34. So several second accuracy of when the event's actually going to happen. And so you stare at this kind of picture for a while, so when you actually look through your telescope, you know you're in the right location. You look for little asterisms, like this one is called Fowler's chair. See, there's the seat and there's the tripod underneath. So you look for this in the sky and you know you're in the right place. So here's an actual image, and it looks remarkably like the planetarium program. There's Fowler's chair. This is how many minutes? 14 minutes before the occultation is predicted to happen. You see the suspiciously double object here. On the left is the star, and on the right is the asteroid approaching the star. This is something called amp glow that I hadn't figured out how to turn off at the time. Now, the plan is to wait until this is just about to happen, like 10 seconds to go on your GPS timer, and then you hit record frames. And my plan was to capture 400 of them, 50 milliseconds long. You want these as short as they can be, so you've got good resolution and time, but you also want to be able to see the event happening clearly. Struggle between the two. We're getting better and better at these short frames. Each occultation is less of a disaster than the previous one. Now here's where it's happening. I hit the capture button at the right time, right about there, according to the GPS. I'm capturing small images, which I've discovered is a lot faster. This is frame number 91, 92, 93. So that's the transitional frame. These are about 60 milliseconds long. So that gives you the time to an embarrassing number of digits when the thing goes out, plus or minus 30 milliseconds. That's pretty good timing. Normally you set up your scope and you wait for an hour for something to happen. Nope, this is fast. So we got a midpoint for this. Oh, and this is coming back on again. Frames 234, 235, 236. Let's see. So that lets you determine the midpoint of the event, which is not 32 or 34 seconds, but 11:00:33.21 with an error of 20 milliseconds. And I send that off to IOTA saying, here's some real good data. You guys may like this. We get the midpoint with 20 millisecond accuracy, 2 orders of magnitude better than the prediction. Right, so we're being really good experimenters here. The actual duration, I said it should be about 6.5 seconds. It was 8.45 seconds with an error of 40 milliseconds. You know, asteroids can be lumpy when they're that small, so maybe there was a lump in the way. So that was successful all the way through. It was just amazing. You turn in your asteroid observation report to IOTA, which looks like that. I did mention Rob Fowler because he also saw it on the Mead. Although you had, where'd you go? You had time slices that were bigger, so mine were still the most accurate. That's what they said they really wanted, was the most accurate measurement. So crank down your time slices, you'll get to be famous. He's got them down to 5 milliseconds now. I don't know quite how you got that to work, but So next time around, I may show you the Meade numbers first and say this.
It was a brighter star, wasn't it?
It was, yeah, it was my fake synthetic star.
Ted,
Yep.
why don't you send them two reports?
Why did I send them? I only sent them one.
You could send them two.
If two people, yeah, if two people join and they both want to turn in their observations, absolutely.
So if you're using the Meade and your Ritchie.
Yeah, yeah, you can join IOTA and submit a report. It's easy, so I'll show you how. So
What was the size of the Meade scope?
Meade is 12 inches,
Okay.
and mine is 8 inches. But the
What was the magnitude of the asteroid?
11.0,
Okay,
pretty bright,
yeah.
and the star was 9.5, pretty bright. So this was a once in a half a year event. So we give awards to people who have attended occultation observation. We especially like this if it's successful. We've given an award for somebody who just showed up and suffered through it. And so I have obtained at enormous expense these Dark Star Awards, which go to just a few people. But if you come out and participate in an occultation, you get to wear one. So, Jim. Congratulations. All right, next comes the surprise.
We're gonna get a picture of you and Jim later.
Oh yeah, well, we have two to do, so we'll do it in a group. Now, the surprise is IOTA posts who says they're going to try to capture an occultation. So here's the asteroid's shadow running across the continent, and here's your little telescope icon. There was somebody in Idaho who was also going to see it. I found that usually the competition drops out, as disasters. The guy in Idaho said he didn't things get set up in time, so he just couldn't capture it. So I thought, well, once again, we're the only place that measured the asteroid occultation that's passing over us. All the rest of the country was asleep. Wasn't true. Surprise! There was another observation. It was not very far away. It was at Norris Lake. Richard Piety, is that how you say his surname? I don't know him very well. Piety? Anyway, he was here for last month's talk, and he decided, well, he'll just set up and try to record it himself, and he did. So at the same time we were doing this at Tau, it was also being observed at Norris Lake in the parking lot. And he found a much longer duration, because he's right, look at this, he's right on the center line. Duration was 13 seconds, plus or minus 0.4. So that's really what you want, is you want several observation sites preparing to receive the asteroid's shadow passing through, because if you get several, you get slices of it, you can see what shape the asteroid had. That's the real exciting thing to do. So if we get a few more people excited by this business, then we'll be able to do sieves ourselves. There's one funny thing, the midpoint differed between our observations. His was 1.2 seconds after ours. But he's 23 kilometers down the path, and the path moves at about 10 kilometers per second. So you expect a 2-second difference. There's plus or minus an unknown systematic as well. I can't see anything inconsistent with his results, although his time slices were half a second. So it's a very coarse grid. But that difference in time was expected. The problem is he doesn't yet use GPS for timing. He's using the CPS clock on his computer. And I've discovered that you can't usually trust those unless you've synchronized it just beforehand. So anyway, this was really neat.
Ted,
Yep.
if you'd like to ask him, Richard is on the Zoom call. Ask him if he'll unmute.
Richard, congratulations.
Thank you, sir.
So, congratulations.
So he is on, I'm watching him.
Thank you.
You're showing Rob, can you turn that on?
This is very impressive, and we look forward to collaborating with you in future. Okay, that was the one where everything worked well. Now I'll try to get through this quickly. This is the recent and terrible return of 785 Zwetana this Monday. First, it wasn't at 11 p.m., which was really civilized of Irene to be late evening. Zwetana tends to be more like 2 in the morning. This is the second time I've observed it. The first time it was like 2:30 in the morning, and this is 1:46 in the morning. So the solar system's about the same. Planets are in about the same position. And it's also up here a little ways out of the ecliptic plane, just like Irene was. Funny thing. There's the path. It's not 150 kilometers wide, but it's 50 kilometers wide. It's still respectable. That could annihilate the entire planet, pretty much. Is 50 kilometers enough?
That's,
Diameter?
that's a Chicxulub size.
Okay, so major change of dominant species after
Oh
10.
boy.
So, but it's safely out of the way. So again, here's the path, there's the green center line, and once again, we're out on, not so far away from the edge. And if you plug in the, assume a spherical asteroid correction, the predicted maximum duration of 2.4 seconds drops to, it should be about 1.6 seconds. All right? Now the challenges, 100% illuminated full moon. I mean, why not make life easy for yourself? Full moon, and I'm going to try to, very short pictures of a rather dim star. The CSC and Astrospheric both predicted clear sky all the way through. So wonder of wonders, it was not a clear sky all the way through. We had to set up, because this was going to be low down and in the northwest, we had to set up on the other side of the Tau building using the sundial pad. Everything there was tilted, so it was an unfamiliar location. My setup table was tilted. Working like this on your computer is not easy. There were ants.
Ravenous ants.
Ravenous ants. Poor seeing. They did agree that it was poor seeing that night. It was 2 in the morning and a low elevation. The event actually took place at 14 degrees above the horizon. So as you can imagine, fluctuate. So this was climbing up Everest by the wrong side. Now here's the beautiful clear sky we encountered. This is about 9 p.m. So you can imagine a lot of this junk, when it's dark, drifting across your star, will just spoil your whole day, right? This is just after midnight. Whoa, there's all this junk around the moon. It was kind of nice having low background light to set things up with. So that was the one good thing, but the full moon is a real
I need to correct
challenge.
the Chicxulub impact, though, it's about a third of the size.
It was a third of the size of, more like 15.
15 to 20 kilometers.
Okay, so if this one comes to visit, it's all over. All right, here we are setting up on the sundial. That way's west. This way's about the right direction. This is Beth wondering what in the world she's doing here. How long do I have to sit here fighting off these ants until something happens? There's the ant protection material. You can see blue cloth lying on the ground with stones on top of it. That actually worked. The ants didn't bother us after that. All right, we're getting there. So here's what one expects to see in the telescope. This is the full field of view, 1120 by 1200 pixels. And at the magic time of 146, I can't read it, 34 or something like that, you see Zwetana sitting right on top of the star. Let's see, 14.3 magnitude asteroid and 11.2 magnitude star. So the asteroid's probably not going to see it. And then 2 bright stars on this side. The asterism you stick in your mind, so you'll be able to recognize it as a check mark. Like that, okay? So let's see if when we actually look, first this is the French database, that Aladdin it's called. And you can see with a real telescope and real stars, same thing, check mark, and this is the target star. So that should be easy to recognize when we get there with the telescope. So looking through the telescope, it's exactly the same thing. I love this telescope. you know, it's Ritchie-Chrétien, so it has no coma, no astigmatism, and no some kind of second order optical error. You just get really sharp round stars out of it. There are veins, so you get little cross lines. So here's the target star, and here's Swetana. This is a 4-minute exposure. So I just stacked 240 1-second maximum gain frames. So I could really have a good, pretty image of the whole star field afterwards. And then I would go looking for where Swetana is supposed to be according to JPL. See if there's any, yeah, that's exactly the right location, which is good. It's sneaking up on the star. It has an hour and a half to get there. Okay, now let's get closer. Here's the screens you watch. This is PhD2 guiding. If you can see this, there's a nice horizontal line there. That's the how good is your heart line showing corrections being made to which way the scope is pointing. It's really close to flat. That's nice. This is sharp cap that shows you what your telescope is seeing at a rather low elevation. And you notice that, well, I don't know if you can tell, this is really enlarged. So like I said, with each attempt, we get a little better with the technology. So instead of taking a full field picture, these fast frames like I used to do, we got it really cranked down to 256 by 128 pixels. That's 1.4% of the full field. The only star in that is, see that little cluster of stuff right near the center? That's the target star. We're waiting for it to go out.
Question, Dave.
Yeah?
Do you keep your PhD on while you're during the occultation?
Yeah. Interesting question, but yeah.
Well, I was just wondering if it might just give it a little pulse right at the wrong time.
It jerks a little bit every so often, but you can see it jerking a little bit every so often within that inner circle. It didn't leave. It was an hour and a half sitting there with nothing going wrong. You go in, you chat with the guys a little bit in the town main building, you come back an hour later, it's still bouncing around in this. I think this is sweet. This equipment's really working well. Okay, so this is how it looked an hour, 20 minutes before I hit the captures. Everything is fine. This is German for it's all cool. Everything is going well. Alles in Ordnung. There's the target star, and you can't see this, but this is the full view, the full screen. And there's a tiny little dot down in the middle of that, which is this region of interest you select, which is 1.4% of the area of the whole field. And that's what it's showing on the screen. That's why the GPS output is in such big characters, is the poor thing has been blown out of all control. But yeah, so it's riding along right in there because of being guided with the guidance program. So you check occasionally, go back in, have a chat, come back again. We decided we would gather around the picture with about 5 minutes to go and watch the event. And Beth was having a nap because it was 2 in the morning. So we woke her up and said, come on, time to watch it. 4 minutes before the event, crash,
Catastrophe.
no star. It's gone. You just see white noise on the screen.
By the way, this is just as I walked up behind him. It was there and disappeared just as I stepped up behind him.
Yeah, so Rob was apologizing for somehow messing it up. He had suggested driving his van around 30 minutes beforehand, and I said, I got a better idea. Why don't you drive it around 30 minutes after the event so nothing will go wrong? So all he did was walk up with his chair and psh, it's gone. This is why I love this area of astronomy so much.
It's exciting.
It's will you have a heart attack now? Or is it coming later? What do? It's vanished. It's just vanished. And your instinct is to say, something stopped working, let me reboot this and that and the other thing. But there's only 4 minutes to go. And I've learned the hard way, the best thing to do is nothing. You just wait. Because it might be a little wisp of cloud that's drifted across your 11th magnitude star. With any luck, it'll drift off beforehand. So what I actually did was I panicked. I said, okay, let's change this. bigger frame size, go from 1.4% of the full field to 34%. I didn't know it at the time of the full field. A tiny little area to a much bigger one. Now my plan had been to capture 100, 200 millisecond frames. Those are kind of long, but we're near enough to the horizon and it was poor seeing, so it was fluctuating around, a little bit of a beehive rather than a sharp image. So I decided to stick with that. I blew up the size of the image and I hit the capture button at the planned time, hoping for the best. For all I knew, because we could see two very faint stars in the screen, but we weren't sure if those were the same ones or not. Could be we had completely drifted away by then, so we had no idea if we'd get anything or not. And I thought, oh, damn, we put so much effort into this. And it was going to be the second observation of Zwetana. But last moment, something went blip, that happens. So, as we've discovered afterwards, it was a small cloud. Just drifting across the star just at the wrong moment. And it would have reappeared if I hadn't done anything to try to repair things at the last moment. But I did repair things, and that turned out to not be so bad. Having somewhat bigger frames gave me other things to focus on, and so here's what they look like. When you just look at the raw frames, it's black with one star, and this is one of the stars in that hook, from off to the left, and it's about 8.0 magnitude. It's bright, but when you stretch the brightness and you stretch the contrast as far as you can. And this is before anything goes out. There it is. There's the target star back at the right location. That's 11.2. This is 11.7. There's another one down here that's 12.1 that you see occasionally. So that's frame 44. And I know exactly when I started timing, just right there. And they were, it turns out they're very close to 200 milliseconds. Even though I was taking a bigger image, maybe that gave it more, it didn't need so much time to move it. For whatever reason, the frames were very close to 200 milliseconds long each. So I knew when this thing went out within the uncertainty of stepping between one frame and the next. Now here we are a bit further along, frame 51, still nothing there. So missing. It's back. It's back at frame 52. So that gave us an event midpoint. Now, they had said somewhere between 146.18 and 146.20, so 2-second uncertainty, and we got it with an error of about 0.1 seconds. So an order of magnitude or a factor of 20 better than the prediction. And the duration, I said it should maybe be 1.4 seconds or 1.6 seconds. It's 1.4 plus or minus 0.01. So that's consistent, and that nails down where it was in the orbit. And those were sent to IOTA yesterday, those numbers.
Is that a cool camera, Ted?
Yes, when I remember to keep it attached. Okay, so we have a success and a new awardee of the Dark Star Award, Beth Bredesen, who, much to her surprise, is now an honored person. Where did Jim go? Jim? Guys next to the big girl here.
Okay, one. She should be in the middle. No, you'll be in the middle. Oh, wow. Two. I have to, thank you.
Got us? All right, thank you, everybody. So let me see if the talk's over. Here's the third talk. This is 2 slides long. We found a funny, screwy blip when you take an airy disk image using the MEAD, and we've been trying to figure out what is the thing that's causing it, and I decided, well, what we really need is just to chop out a mask. So I went by the art store and got some cardboard, black cardboard, and chopped out a mask to see if that gets rid of the blip you see in airy disks. And here on the left, you see it works. There's the airy disk with the mystery damage from somewhere on the front of the aperture. And when you chop out that little mask and put it on, you get an airy disk without any crap in it, like that. The reason you don't want that stuff is when you focus the image of a star, it's the Fourier transform of this image. So a bright region like that will give you rays coming down that really distort the image of the star. As you can see, there's rays coming off to the lower right. Once you put on the mask, you get a much sharper star image, but you lose about a magnitude. So we really should find what's causing that. That's the shop talk. All right, so that's everything. Thank you for listening.